Okay, so for like the longest time, when we talked about making AI better, faster, smarter, the main playbook was just scale it up, right? Make the model bigger.
Absolutely. That was the dominant trend. We saw this incredible explosion from models like BERT with millions of parameters to, these huge LLMs and multimodal models, hundreds of billions pushing towards trillions of parameters.
And it worked.
Mhm.
For a good while, bigger genuinely seemed to equal better performance.
It did. The compute costs scaled, well, roughly linearly with the number of parameters. So naturally, if you wanted efficiency, you focused on the model itself.
Right, that's where things like pruning, quantization came in,
Yeah.
model-centric stuff.
Exactly. Pruning bits off, shrinking the numbers with quantization, knowledge distillation.
Mhm.
It was all about making that model, that brain, smaller and leaner.
But this paper we're looking at argues something pretty fundamental changed.
It really does. What's fascinating, and this is key to the paper's argument, is how quickly that cost dynamic shifted. Around mid-2024, maybe a bit earlier, we started hitting, let's say, practical limits on just making models bigger.
Hardware constraints, training costs, getting astronomical.
Yeah, things like that. Model sizes began to plateau somewhat, but the data the models were being asked to handle, that just kept ballooning exponentially.
Ah, okay. So the model size kind of levels off, but the input length goes through the roof.
Precisely. Context windows for text got massively longer. Think reading whole books. Image resolutions needed for MLLM shot up to 4K and beyond. Video, we started talking about processing, huge numbers of frames.
So the bottleneck shifted. It wasn't just the model size anymore.
Exactly. The paper argues the main computational headache, the real resource hog, became processing these incredibly long sequences of data, these tokens, and specifically the cost associated with the attention mechanism.
Attention, that's core to how transformers worked, right?
Right.
Letting the model weigh the importance of different parts of the input relative to each other.
That's the one. But it has this characteristic cost. If you have a sequence of N tokens, could be words, image patches, video frames, standard attention needs to figure out the relationship between every single pair.
So n times n interactions.
Roughly, yeah. N squared. Which means if you double the sequence length, the compute cost doesn't just double, it quadruples. 10 times longer, 100 times the cost.
Ouch. That's the quadratic scaling problem.
That's it. And when you start dealing with sequences measured in millions of tokens, that quadratic cost just becomes overwhelming. That's the new bottleneck this paper focuses on.
Okay, I think I get the quadratic cost now. It just explodes. Can you give some concrete examples from the paper of just how much these input sizes have grown?
Oh, definitely. They point to LLMs going from, say, Llama 1 handling maybe 2,000 tokens.
Which seemed like a lot back then.
Right. To models like Llama 4 Scout handling, get this, 10 million tokens.
10 million. What does that even let you do?
Things like super long chain of thought reasoning, analyzing massive code bases, running complex multi-agent simulations where agents need long histories. Then in multimodal, you have models like Intern VL3 needing to process 4K images, or Video XL Pro crunching through 8,000 frame videos.
And generation, too.
Yeah, generative models creating photorealistic 4K images like PixArt Sigma, or even pushing towards generating hour-long videos like the potential suggested by models like Sora.
Wow. Okay, so all this amazing capability handling these huge contexts, it comes back to bite us hard on the compute side because of that n-squared attention cost.
That's the crux of it.
So if making the model smaller isn't the primary answer anymore, what does the paper say we should be doing?
This is the core argument. If the problem is the exploding data sequence length, the paper posits that the solution needs to be more data-centric, not just model-centric.
Data-centric, okay. Focusing on the input itself.
Exactly. And within that broad idea, they really zero in on token compression.
Token compression. Tell me more.
The fundamental idea is pretty intuitive, actually. Instead of just letting the model deal with this massive, potentially redundant sequence of tokens, you try to shrink that sequence first. Identify and remove or condense the less important bits before it hits the main computational bottleneck.
So compressing the input stream.
Precisely. And a really crucial point the paper makes is that many of these token compression techniques can be applied without needing to change the underlying model architecture.
Oh, interesting.
And often without even needing to retrain the model, which is a huge potential advantage in terms of cost and practicality.
Okay, that sounds really appealing. Sort of
Yeah.
like pre-digesting the information to make it easier for the model's brain to handle.
That's a decent analogy, yeah. And the paper breaks down how current methods generally do this in a sort of two-stage process. First, you need to decide which tokens you're going to target for compression.
How do you figure that out? Which ones are important or redundant?
That's the compression criteria stage. You need some way to score tokens. The paper outlines two main families of approaches. First, parametric methods.
Meaning they add parameters.
Usually, yes. They might use small auxiliary neural networks that run alongside the main model, specifically trained to predict the importance score of each token. These helpers can be trained with the main model, or you might use a pre-trained one just for scoring, which would be training free in terms of not needing to train it for this specific task.
Okay, helper networks. What's the other way?
Non-parametric methods. These avoid adding extra learnable parameters. They rely on heuristics or rules. Sometimes they cleverly use calculations the model is already doing as part of its process.
Like what?
Like the attention weights themselves. Remember, the model calculates how much each token should attend to others. Those weights can be repurposed as a rough proxy for importance.
Using the attention calculation itself to decide what to compress. Clever.
It is, though we'll touch on some potential issues with that later. Other non-parametric methods might use external calculations, like measuring the cosine similarity between token embeddings to find tokens that are very close in meaning and therefore potentially redundant.
Okay, so you score the tokens using either helper networks or some parameter-free rules, maybe based on attention or similarity. Then what? How do you actually shrink the sequence?
That's stage 2, the compression strategy. Based on the scores, you transform the original sequence into a shorter one. The paper highlights two main strategies here. The most straightforward is token pruning.
Just deleting them.
Pretty much. You set an importance threshold, and any token scoring below that just gets dropped from the sequence. Simple, direct reduction in length.
But I guess you risk losing information.
That's the major drawback, the paper notes. Especially for tasks needing fine-grained detail, just chucking tokens out might be too blunt an instrument.
So what's the alternative?
The other main strategy is token merging. This is a bit more nuanced. Instead of just deleting low-scoring tokens, you try to combine them with nearby, semantically similar tokens. Often this involves a weighted aggregation, where the importance scores guide how much each original token contributes to the new merged token.
So you're sort of blending related ideas together.
Exactly, like summarizing. The idea is to preserve more of the original information compared to just pruning it away. The paper mentions techniques like tome token merging as examples of this.
Okay, so score the tokens, then either drop the unimportant ones, pruning, or blend them together, merging. It really does feel like trying to get the essence of the input.
And the payoff, if you get it right, can be significant. The paper emphasizes benefits during both training the models and using them for inference.
Let's talk training first. How does shrinking the input help there? It seems obvious it would be faster, but is there more to it?
There is, actually. Firstly, yes, efficiency is a big one. Reducing sequence length from n to m gives you that quadratic speedup in the attention calculation. Computation drops by roughly m squared over n squared. Memory use drops too, linearly, m over n. Faster training, potentially bigger batch sizes.
Right, the direct speed and memory gains.
But the paper also highlights potential quality improvements. By focusing the model's attention during training on the most informative tokens, maybe by using these scoring methods or other techniques like deduplication to clean up the training data, you might actually train a better model.
So cleaning up the training data itself through a compression lens.
Sort of, yeah. They also frame certain data augmentation techniques like mixing parts of images or replacing words with synonyms as a form of token manipulation that fits this compression paradigm and can improve robustness.
Interesting. Okay, so better training data potentially and faster training cycles.
Yeah.
What about when you actually use the model inference time?
Similar benefits, really. You get that same potential for quadratic speed up in computation because you're feeding the model a shorter sequence.
Which means faster answers for the user.
Exactly. And critically, as we mentioned, many of those non-parametric methods can often be applied directly at inference time without any retraining. That's huge. You can potentially take an existing model and speed it up just by adding this pre-processing compression step.
That's a massive plus. Any other inference benefits?
Memory reduction is also key, especially for large language models because of the KV cache.
The KV cache. Explain that again quickly.
Sure. When an LLM generates text, token by token, it needs to remember the context. It stores intermediate key and value states calculated from all the previous tokens to compute the attention for the next token it generates. This memory storage is the KV cache.
And it grows with the sequence length.
Linearly, yes. The longer the sequence you've processed or generated, the bigger the KV cache gets. It can become a real memory hog, limiting how long sequences you can handle or how many users you can serve concurrently. Token compression, by reducing a sequence length directly reduces the size of the KV cache, again, by roughly m over n.
Wow. Okay.
Haha.
Faster inference, less compute, less memory, and it specifically helps with that KV cache bottleneck for LLMs. That really does sound like a suite of powerful advantages.
The paper summarizes it nicely into 5 main points why token compression is so compelling right now. 1. Universal applicability redundancy is everywhere. Text, images, audio, video.
Makes sense.
2. Dual-phase efficiency, it helps in both training and inference. 3. Architectural compatibility, it often slots into existing models and works alongside other efficiency tricks.
It doesn't require total redesign.
Often not. 4. Low implementation costs, especially for those training-free non-parametric methods. And 5, the big one, quadratic gains, it directly tackles that n-squared attention cost, the main bottleneck in this long context era.
Universal helps both phases. Compatible low-cost quadratic gains. Yeah, you can see why researchers are excited about this.
Yeah.
But I sense a but coming. It can't be that easy. Right?
You're right. There are definitely significant challenges. The paper is quite clear about these. It raises the question, are we actually compressing the right things? And are we even measuring success properly?
What are the main roadblocks then?
A major one is performance degradation. Sometimes applying these methods hurts the model's accuracy more than you'd expect, or in unpredictable ways.
Why? What goes wrong?
The paper points to a few things. Methodological bottlenecks, for one. Remember we talked about using attention scores to decide importance?
Yeah, seems clever.
Well, the paper flags that attention scores can suffer from things like position bias. A token might get high attention just because it's near the end of a sentence or in the bottom right corner of an image, which has nothing to do with its actual semantic importance.
Oh, right. So the score isn't really reflecting true importance.
Exactly. And if you prune based on those biased scores, you might throw away crucial information. In fact, the paper mentions a really interesting kind of counterintuitive finding, possibly shown in their figure 2, that some carefully designed attention-based compression methods actually performed worse than just randomly pruning tokens or using simple pooling.
Wait, random pruning beat a supposedly intelligent method? That sounds backward.
It does, but it highlights how tricky relying on these potentially flawed heuristics like raw attention scores can be. There are also inherent limitations. Token compression just isn't suitable for all types of data or tasks.
Like what?
Think about tasks like detailed visual grounding or optical character recognition, OCR, on a densely patched document. Almost every token, every character, or pixel patch carries unique, vital information. There's just not much redundancy to compress.
Or maybe audio.
Exactly. Audio signals, represented as tokens for automatic speech recognition, ASR, are often very dense and continuous. Chopping out or merging tokens can easily disrupt that continuity and just mangle the signal.
Okay, so choosing the right tokens is hard because of biases. And some data just isn't compressible without losing too much. What else?
Another big challenge is ensuring suboptimal token representation. Many current methods focus on preserving information needed to reconstruct the original input or information relevant to one specific training task. But the paper argues that doesn't mean the compressed tokens are the best representation for enabling the model to perform well on a variety of downstream tasks or to generalize to new situations. Redundancy-based methods might keep reconstructive details that aren't actually useful for, say, classification. Importance-based methods might bake in biases from the specific training task, hurting flexibility.
So the compressed version might be okay for the original job, but not great if you ask the model to do something slightly different with that information.
That's the concern. And finally, there's a major challenge around fair comparison and evaluation. How do we actually measure if one compression method is better than another?
Don't we just look at FLOPs or compression ratio?
That's often what's reported, but the paper argues we need to rethink metrics. Lower theoretical FLOPs or a high compression ratio don't always translate into actual real-world speedups.
Why not?
Implementation details matter hugely. Maybe the compression method interferes with optimized low-level kernels like flash attention. Maybe the overhead of calculating scores or merging tokens layer by layer eats up the savings. The paper strongly advocates prioritizing actual runtime latency as the key metric.
What you actually experience.
Exactly. And related to that is the benchmarking gap. Our current standard AI benchmarks, the tests we use to rate models, often aren't sensitive enough to the kind of information loss that token compression might cause.
So
The paper cites studies where models showed surprisingly minimal performance drops on benchmarks, even with very high compression rates. This suggests the benchmarks aren't properly penalizing the loss of fine-grained detail. We lack benchmarks with enough task diversity, especially tasks that rely on that detail, and metrics specifically designed to evaluate compression trade-offs.
that makes a ton of sense. If your measuring stick isn't good enough, you don't really know if you're making progress or just, getting lucky on a test that doesn't catch the problems.
Precisely. It's hard to improve if you can't reliably measure.
So, given all those hurdles, tricky important scoring, inherent limits, representation issues, and the big measurement problems, where does the paper suggest we go from here? What's the future work?
They propose a couple of key directions. One is embracing data model-centric co-development.
Meaning using both approaches together.
Yes, instead of seeing it as an either between compressing the data or compressing the model, the future is likely in combining them intelligently. It could be as simple as doing one then the other, or more sophisticated, where insights from analyzing data redundancy patterns could actively inform how you prune the model, and maybe the model structure could inform better data compression strategies, a kind of mutual reinforcement.
A more holistic view of efficiency.
Exactly. The other major push, directly addressing the measurement problem, is the need for dedicated benchmarks for token compression.
Building better measuring sticks.
We absolutely need them. New benchmark suites designed from the ground up to evaluate token compression. They should cover diverse data types, text, vision, audio, multimodal. They need to include tasks specifically chosen because they are sensitive to information loss. Think OCR, detailed visual QA, maybe speech translation where nuance matters. And crucially, they need to report both task performance and real-world runtime latency together.
So better collaboration between data and model techniques, and much better ways to test if it's actually working well in the real world. It sounds like there's still a lot of exciting work to be done.
Definitely. It feels like an area with huge potential, but we're still figuring out the best practices.
Now, the paper also touches on alternative views, right?
Yeah.
Does everyone agree this data-centric shift is the main path forward?
No, and it's important to acknowledge those. The paper briefly engages with counter-arguments. One perspective is that model-centric compression is superior.
The established methods.
Right. Some argue they're more mature, better understood, and perhaps more reliable, especially when you need to deploy models on very resource-constrained devices. The concern is that token compression, by altering the input, inherently risks losing critical context that model pruning, which just slims the network, might preserve. They might point to methods like dynamic VEAT, which adapt the model's compute based on input complexity.
What's the paper's response to that?
The counterargument leans on scalability. Model-centric methods might hit limits with truly massive data inputs, whereas data-centric approaches tackle that load up front. Plus, the potential for low-cost, training-free data compression is appealing. Ultimately, the paper suggests combining them is probably best.
Okay, what's the other main alternative view?
It's the argument that advanced architectures are more promising. The idea here is that newer model designs, like state space models such as Mamba, or transformers using clever tricks like window detention, swing transformers, are just inherently better at handling long sequences efficiently.
So maybe we don't need aggressive input compression if the architecture itself is smarter.
That's the gist of the argument. Why compress the input if the model can handle the long sequence efficiently anyway?
And the paper's take on that.
The counter is that even these advanced architectures still require significant compute, especially for training. Data compression can reduce that load before the data even hits the fancy architecture. Also, these approaches aren't mutually exclusive. Token compression can often be used on top of advanced architectures to get further efficiency gains. They can be complementary.
It's really good to see those different perspectives laid out. It shows this is an active area of research and debate, not just a settled conclusion. There are multiple paths being explored for AI efficiency.
Absolutely. It's a dynamic field.
Okay, so let's try and wrap this up. We've seen a deep dive into this fascinating position paper arguing for a pretty major pivot in AI efficiency research.
Yeah, moving from primarily focusing on shrinking the model-centric view,
To focusing on shrinking the data input itself, the data-centric view, specifically through token compression.
driven by the fact that the sheer length of data sequences models now handle, combined with the quadratic cost of attention, has become the new primary bottleneck.
And token compression tackles this by finding ways to score tokens for importance or redundancy, and then either pruning the less important ones or merging similar ones together.
Offering some really compelling potential benefits. Speeding up training and inference, cutting down memory use, crucially optimizing that LLM KV cache, maybe even improving training data quality. Plus, it's often compatible with existing models and can offer those quadratic computational savings.
But as we discussed, it's definitely not a silver bullet. There are real challenges.
For sure. Performance degradation from issues like position bias and scoring methods, inherent limits for certain dense data types, ensuring the compressed representation is actually useful for diverse tasks, and a huge need for better metrics and benchmarks that reflect real-world latency and information loss.
The way forward seems to involve combining data and model compression smartly and, critically, building those better benchmarks to guide the research.
And acknowledging that there are still strong arguments to be made for continuing to improve model-centric methods or focusing on architectural innovation as alternative or complementary paths.
It really does feel like we're in a new chapter for AI. Dealing with the sheer scale and length of information is becoming just as critical, maybe even more critical in some ways, than just building bigger and bigger models.
The information deluge is real for AI and for us.
That makes me wonder. Think about all the data we process every day, not just AI. How much redundancy is there in the articles we read, the videos we watch, the conversations we have? If we, or our tools, got really good at this kind of token compression for human information streams, how might that fundamentally change how we learn and interact with the world? Something to chew on.
That's a thought-provoking question.
Well, thanks for joining us on this deep dive. We hope you found these insights into the shifting landscape of AI efficiency valuable.